All right, so this is example 7.18 from Potter's book, and it says, estimate the flow rate in the simple piping system in the figure, that's this figure, if the pump characteristic curves are shown in this figure. Also, find the pump power requirement. So that's good. We're going to look a little bit at pump power, which is something we haven't covered in class yet. But first, let's try to estimate the flow rate. So this is a simple system. You have a reservoir, another reservoir, water at 20 degrees Celsius, and you are installing this pump in order to transport water from the lower reservoir, which has an elevation of 60 meters, to the higher reservoir, which has an elevation of 90 meters. Okay? If this pump were not here, obviously water would flow from this reservoir to this reservoir. But we're adding the pump in order to reverse the flow rate. Okay? So the first thing we need to understand, or we need to know, is that when we're selecting a pump or designing a pump for a system, it's very, very common to assume steady uniform flow. So why do we assume steady uniform flow? Because that allows us to use a simplified form of the energy equation for steady uniform flow. So when you see this problem, the very first thing you want to do is you want to write your energy equation for steady uniform flow. So I'm going to write down, go ahead.
There's just a really big echo. I was wondering if we can work on pausing or muting our mics.
Yeah, somebody has a little bit of feedback. Let me see who it is. We can just mute that person. Oh, never mind. Everybody muted themselves.
The guy just muted. It was good. It's good. It's I don't know what his name was, but it's FNU.
Oh yeah, Habib. It's you, Habib. Mute your microphone. Everybody else, you're fine. All right, so the very first step is to write down the energy equation for steady uniform flow. If you guys forgot that equation, that's okay. I remember it because I know. The energy equation for steady uniform flow. We have the pressure term at the inlet control surface, the velocity term at the inlet control surface, the potential term at the inlet control surface, and the pump head equals all those energy terms at the outlet control surface, the turbine head, and the head losses, if any. Okay, so this is what we have. This is our system. This is the equation we have for now. This is a simple system. Are there any turbines in this system?
No.
All right, good. Make sure to unmute your mics when you're about to speak. Good. Where do you think is the best place to select our control surfaces?
The top of the reservoirs.
Exactly. We have no data from here to here or from here to here, so really the best thing to do is to find the top of the reservoirs. This is 60 meters and this is 90 meters with respect to a datum, but we don't know what that datum is. Okay? So we're going to choose the top of the reservoir for our control surface. What is the pressure at the top of the inlet control surface? First of all, which one will be the inlet? Would it be the left or the right?
The right.
The right. Okay? Because flow will travel from this lower reservoir through the pump into this higher reservoir. So this would be our inlet. So what's the pressure there?
It's just atmospheric.
Atmospheric pressure. Good. What's the pressure at this point?
Atmospheric.
Okay, so we have the same pressure, we have the same specific weight, so the pressure terms will cancel out. Big reservoir, right? So if it's a big reservoir, what do you think is the velocity of this control surface? 0. Exactly, we can approximate it to 0, very, very small. What about this one?
Same.
0, good. So we kind of try to simplify our equation as much as possible, and I think that's good. This is a good simplification. We want to solve for the pump head because this pump head is the required pump head for the system. So I'm going to solve this equation for pump head, and I'll get that pump head will be equal to elevation at point 2 minus elevation at point 1 plus all the head losses. Now we know that head losses are a function of friction loss and minor or component loss multiplied by the kinetic energy head through the pipe. So this is our equation, okay? Now we got to deal with what we have and what we don't have. Do we have Z2?
I got a quick question.
Yeah, go ahead.
So this doesn't account for the back pressure of the higher elevation reservoir, does it?
It does, and that it's the differential in water surface elevation that accounts for it.
Okay,
All right.
gotcha.
So, for example, if we would have been given information for the elevation of this pipe, we could have chosen our points at the inlet and outlet of the pipe. Velocities and elevation will cancel out, but then you would still have a differential in pressure. Since we don't do that, our differential won't be in pressure; it'll be in elevation. Does that make sense?
Yep.
All right, thanks, Darby. Okay. So let's look at what we have. Let's look at what we don't have. In this case, we have our elevation of the control surface at number 2. That's 90 meters. Our elevation of the control surface at 1. That's 60 meters. We don't have the friction factor yet, but we can estimate the length at which the friction is occurring, right? What would that length be?
400.
Exactly, right? The length is occurring over the friction is occurring over a length of 400 meters of pipe, so 400 meters. And then we have the diameter of the pipe, which we can use in our friction calculation. So our diameter is 20 centimeters. All right? Now to this, we have to add whatever minor losses are occurring. So what coefficients do you see here? Or sorry, what minor components do you see here?
Should just be the entrance, the exit, and the pump.
All right, we have the entrance, right? This is 1. We have the exit, this is 1. I'm not going to count the pump as a minor coefficient because whatever changes in energy occur through the pump are going to be quantified here.
Oh, okay.
All right? So, but I will quantify the entrance and the exit. So you guys have tables, right? So what was the typical entrance loss coefficient? Let's say that these edges are sharp. So what would that K coefficient be?
0.5 and 1.
Yep, 0.5 for the entrance. And for the exit, it's almost always going to be 1 for this type of exit, okay? So we have our minor loss coefficients. We can write them down in our equation. So we have 0.5 and we have 1. And this is multiplied by the kinetic energy head. Now, we don't have any velocity. And we don't have flow rate, because that's what we have to estimate here. So what we're going to do is we're going to leave our velocity as a variable, but I don't want to express it as velocity, because everything else I'm given is in terms of flow rate. I want to express this as flow rate. So I'm going to write down the relationship between velocity and flow rate. Remember, velocity or average velocity is equal to flow rate over area. This is uniform flow, so the velocity at any point in the control surface or in the pipe should be equal to the average velocity. This is steady flow. That means that the flow rate will remain constant with time. So we can treat these two as constants, and then the area would just vary depending on the area of our pipe. In this case, our pipe has 20 centimeters, it's just one pipe. That means that all these three terms will be constant: velocity, flow rate, and area. So instead of this velocity squared, I want to replace that velocity with a flow rate over area. So that gives me an unknown flow rate squared. All right? And that is divided by 2 times gravitational acceleration times the area squared. In this case, my pipe has a diameter of 20 centimeters, so my area will be equal to pi over 4, 20 centimeters squared, and the whole thing also has to be squared. All right, so far so good. Let's go ahead and simplify this a little bit. Let's see, I have 90 minus 60, so I'll get that my pump bit is equal to 30 meters. plus my friction factor. How much is 400 divided by 0.2?
Oh, never mind.
It is 2,000, yeah.
Plus 1.5. Right? 0.5 times 1 is plus 1 is 1.5. And then I have my unknown flow rate here. And I'll have 2 times 9.81 times pi over 4 times 0.2 squared, all that squared. Somebody get that. I'm going to try to use my calculator as well, see if I can get it first.
0.19.
No, I'm going to get it first.
0.0.
No, I'm going to get it first.
4164.
I got it. It's okay, guys. I got it first. 0.019364.
So it's 0.019364.
Guys, you better let him get it first next time, or else he's gonna kick you out of the class.
That's true. How I did with David. Let's see. This is meters second squared. This is meter squared. So meter squared per second squared. Awesome. We did it. Did we? Yes. We did it. Okay. So this is what we have so far. We don't know F. We don't know Q. Now, typically, you want to run this through a computer program because the friction factor, right, depends on the Reynolds number, which depends on the velocity, which depends on the flow rate. So as Q changes, F will change. However, we're going to simplify this system as much as possible so we can actually plot it here without needing to use a computer. So I'm going to add one simplification, all right? And I'm just adding this to make my problem a little bit easier. Well, actually a lot easier. We're going to assume fully turbulent flow, which in the case of flow through a pump, that is a pretty safe assumption to make. So why would I assume fully turbulent flow? How does that help me?
You can use the Moody diagram.
Exactly. I can use the Moody diagram and I won't need the Reynolds number, which means that my friction factor will no longer be a function of the flow rate. So I can get one friction factor value to use in my equation. So if I want to find the friction factor assuming fully turbulent flow, normally I would first find the velocity and the Reynolds number, but it's fully turbulent flow, so we don't need it. What's the other parameter that I need to find to use the Moody diagram?
The roughness height.
The relative roughness, right? Specifically the relative roughness. Good. We know that this is a wrought iron pipe. So for wrought iron, my roughness height is 0.046 millimeters. Therefore, my relative roughness will be my roughness height divided by the diameter, which is 20 centimeters. I'm just going to call it 200 millimeters, so I can just cancel these out. Okay? So, this gives me a relative roughness of how much?
0.00023.
Yep. And dimensionless, right? Because millimeters cancels out with millimeters. Now, I can go to my Moody diagram, and using only this relative roughness, I can find a friction factor. So I have my textbook here, which means that I have my Moody diagram here. Our relative roughness was 0.00023. So that means I'm going to have to zoom this out a little bit. Oh, I can't zoom out. Never mind. 0.00023.
Over part of the diagram.
What?
There's a thing that says recording over part of the diagram.
I'm sorry, does that not allow you to use the Moody diagram? Is that better?
No, I think you just have to move your cursor over to the side or something. I think your cursor's on the screen.
No, we can still see mostly through it. It's still readable.
Alright. So it's okay, you guys have your own Moody diagrams, right? So you can do this at home. So we got 0.00023 somewhere just above this light blue line. we're assuming fully turbulent flow, which means that my Reynolds number will be somewhere around here. So it really doesn't matter what the Reynolds number is because my friction factor won't change. I draw a straight line to the left and I can get a friction factor of approximately, I don't know, 0.014, 0.015-ish. I'm going to say 0.014. Yeah, 0.014. Alright? You guys can try to do that yourselves. Again, the friction factor doesn't have to be so precise, but I think 0.014 is actually a good approximation because 0.014 in that Moody diagram was actually just one of the lines. So I just approximated to the nearest line. So from the Moody diagram, I get that my friction factor is approximately 0.014. Because I'm assuming fully turbulent flow, this friction factor will remain constant. It won't change with the flow rate. What that means is that my pump head for the system should be equal to 30. All right. Oh, this is actually wrong. This is meters times meters squared. So that should be meters to the 5th, I think. There we go. So my pump head will be equal to 30 meters plus my friction factor of 0.014 multiplied by 2000 plus 1.5 divided by 0.019 meters fifth per second squared, and then multiplied by my unknown flow rate squared. At this point, I'm just going to ignore the units because I know this is dimensionally homogeneous, right? This will be meters to the 6th divided by second squared. So meters to the 6th divided by meters to the 5th is just meters. So my final answer will be in meters. All right. So can anybody plug this into a calculator and give me that value?
1582.63.
1582.63.
I did plus 30 as well.
All right, let's not do that.
Would it be 2210.5?
Can somebody confirm that?
I got 1552.
I like
Yeah,
that
I got
better.
the same thing.
I also got 1552.
All right, so I'm going to do 1552.
That is a times and then a plus on the numerator, right?
Sorry? Yeah,
That
this is a
multiply
times,
and then add.
and this is plus. PEMDAS, right?
Yeah.
Awesome. So this is my equation for the pump head for the system. Does this equation tell me the flow? No, it's still a variable. But now that I have the equation for the pump head for the system, I can compare it to the performance of this pump in order to find that flow rate. And here's where things get a little bit graphical. I mean, it was already graphical with Moody, but essentially we want to plot this equation on this pump performance curve. Notice that this curve relates pump head to flow rate. This equation relates pump head to flow rate. So we can just plot this equation. The flow rate here is in cubic meters per second and the pump head in meters, which is good because we have the same dimensions here. So we can go ahead and plot. Now, the reason why I chose my friction factor, or I tried to simplify my friction factor to be constant, is so that it's easier for us to plot. However, when you're dealing with actual work, you want to be as precise as possible, you don't have to make this assumption. You can just write a small code that relates friction factor to the flow rate by the Reynolds number. And you can do that by using any of the empirical equations that exist for the Moody diagram. But we can talk about that later. That's not really part of this class. So let's go ahead and plot this equation, 30 plus 1552q squared. Let's plot it here. And I'm going to plot it with my red Sharpie. First of all, it's 30 plus 1552. That means that when q equals 0, the pump head will be equal to 30, right? Yes. To this, we have to add 1552 times q squared. So that's a quadratic equation. Is that what you call it, quadratic? No. What do you call it? It's a power equation? Something like that. I would say...
Exponential? No, not exponential.
Something like that. I don't know. I would say, if you want to plot this, just choose 3 arbitrary values. For example, you can choose q equals to 0.1, 0.2, and 0.3. Find the pump head, and then just trace a curve, trace a line over it. So, can somebody give me...
Wait, a question.
Yeah, go ahead.
What does the little HP mean then? So why
So,
head pump that?
yeah, let me actually change this to positive. So this is not a standard nomenclature, but I'm trying to use uppercase HP when it's related to the pump itself, and lowercase HP when it's related to the system. Okay? So this means that for this pump, at this flow rate, the pump will produce this pump head. Okay? However, for the system, it'll be different. For the system, at this flow rate, the system requires this pump head, and they may not always be the same. In fact, you'll see that they're only the same at one point. Okay? So that's what it is. This is related to the pump. The equation we just got relates to the system. Notice that the equation we just got had nothing to do with this graph. We're actually joining it, combining it with this graph now, so we can find the actual performance of that pump. Does that make sense?
Makes sense.
Cool. All right, so somebody give me the value for the system demand. This is the system demand when the flow rate is equal to 0.1.
45.52.
45.52? 45.52?
Yes, sir.
Oh, perfect. So that means that when the flow rate is equal to 0.1, was that Michael?
Obviously.
Okay. Then my pump head required will be 45.52. So it's somewhere around here. What about 0.2?
92.08.
92.08, so somewhere around here, right? Let's pretend that my lines are straight. And 0.3?
It's off the graph.
It's under
It's
900.
169 or
Yeah.
170.
So somewhere around here. Good. Now why am I drawing this one? Because I want to get a good feel of what my curve will look like. Something like this. This red curve is the system demand curve. That means the amount of pump head required for a specific flow rate. This blue curve is the pump performance curve. That is the amount of pump head supplied for a specific flow rate. When can this pump operate? This pump operates when the amount of pump head required is equal to the amount of pump head supplied. And when does that happen? When the red and the blue curves intersect. Okay? So we're going to find that intersection point, which is somewhere around here. And we're going to call this the operating point. Once we found the operating point, we can use it graphically to determine or approximate the flow rate and to determine or approximate the pump head. Now, since we already have this equation, we can approximate the pump head first and then use this equation to find the flow rate, or vice versa. We can approximate the flow rate first and then use the equation to find the actual pump head so that our results aren't too different. Okay? So, what do you guys think? Is it point, I don't know, it feels like 0.18-ish to me for the flow rate. All right? So I'm going to approximate my flow rate, my operating flow rate, as 0.18 cubic meters per second. For an operating flow rate of 0.18 cubic meters per second, we're going to have a pump head of approximately how much?
It's like 78, I think.
I got 80.285.
Good. So our graph is a little bit off, but it's okay. After we find the operating flow rate, the operating pump head, we can actually find the efficiency. Now, how do we do that? This green curve is the efficiency curve. It relates the efficiency, which is on the right y-axis, to a given flow rate. So if we already have our flow rate of 0.18, all we have to do is find out where this flow rate intersects with the efficiency curve, which is a little bit above my operating point, so somewhere around here. Straight line to the right, and I get an approximate efficiency of, I'm going to say 85-ish%. So my efficiency will be approximately 85%. That means that for every 1 unit of energy that the pump requires, only 85% of that is actually outputted by the pump into the system. So, before I do the final step for this problem, are there any questions? Okay, if there are no questions,
Sorry, actually, Evan does have one. It's
he can unmute his mic
wait.
if he wants.
I think it's good. I think Darby got it.
Awesome. Thank you, Darby. Do you mind sharing the question, though, so that whoever watches the video
Yeah.
can benefit from it?
Evan asked why the efficiency point was above the P. So I think he's trying to figure out exactly what their relationship is there. And my answer to him was that it was because OP was under the efficiency line. So you had to go up above OP to hit the efficiency.
Exactly. If my OP would have been here, then my efficiency line would have been up here, right? So
If OP had been to the left of it, wouldn't you have to go down?
exactly. If my OP would have been here, my efficiency line would have been here. Because the efficiency line relates flow rate only to efficiency. Has nothing to do with the pump head itself, right? Yeah, thank you for sharing that. Before I finish this problem, there are a couple of notes. We have this flow rate, right? But we got this flow rate assuming that the flow was fully turbulent. So when you get to this point, you would want to check if your assumption was correct. Now, how do you check if your assumption was correct? Well, you can find the friction factor using that flow rate. So you can say that the friction factor is a function of Reynolds number and relative roughness. And now that you have a flow rate, you can find the Reynolds number. You do that by multiplying velocity times diameter over kinematic viscosity, but velocity is just flow rate over area. So you want to find your Reynolds number. You want to find your relative roughness again, which we already got it. It was 0.00023. And using that, you can then use the Moody diagram to find an approximate value of F. We're not going to do that for this problem, but typically that's what you would have done in order to know if your fully turbulent approximation was correct or not. All right? Now, the next thing they want us to find is the pump power requirement. So we're going to look at a little bit of kind of new theory, but not really. So if you guys remember when we were deriving the energy equation, before we had everything in terms of, or in dimensions of feet, we ended up with pump power, I think that's what it was, and turbine power and other terms in our energy equation. This was back when we derived it in class. And in order to convert this to feet, I think that we divided everything by mass flux times gravity. Now, I don't remember if that's correct or not, but basically, what are the dimensions of power? Power is work over time, right? and work is force times length. So this would have been force times length over time, and force is mass times length over time squared. So I'm going to do a quick look at the dimensions quickly to make sure that this was correct, but essentially power is mass times length over time squared times length over time, I think. Is that correct? It's force times length over time power. I think so. Mass flux is mass over time, and gravity is length over time squared. Let's see, my mass cancels out. I got time cubed, it all cancels out. And then one length cancels with another length, and I end up with a length. Yes, so this is what we did to convert my pump power to a length. So that means that this was equal to pump head. And this is how we derived that in class. Now, what we're going to do when we're asked to find the pump power requirement, we need to take this pump head and go all the way back to pump power. So we're not really dealing with mass flux, but we are dealing with flow rate, and our flow is steady and uniform. So we can express our pump head as equal to the pump power divided by mass flux. Flow is steady and uniform, so mass flux is just density times flow rate. And then gravitational acceleration. Density times gravitational acceleration is what fluid property?
Specific weight.
Yep. So we get this expression for pump head and pump power. All right, so here's my expression. Pump head equals pump power over specific weight times flow rate. This means that if I want to solve for pump power, that should be equal to pump head times specific weight times flow rate. Now, when you're asked to find the power requirement for the pump, this is the equation that you turn to, but you also need to remember that we were given an efficiency of 85% for this pump. Now, what does that efficiency of 85% mean? That means that whatever power came into the pump divided, whatever power the pump produced, there we go, divided by whatever power came into the pump should be equal to 0.85, because the pump can only produce 85% of the power that it received from the electrical source. Now this is because, well, that's just the way things work, right? There are losses in energy that occur throughout the pump. Now, Darby, just remember you were talking about the minor component through the pump. We don't really need it, again, because we quantify it in the pump head, and that itself is eventually included as part of the efficiency. So any energy loss that occurred throughout the pump is accounted for with this efficiency. So now, if we want to find the power requirement for the pump, that is my power in. So my power requirement for the pump for this problem, power in, should be equal to the power that the pump produces, which is just the pump power, divided by the efficiency. We know that the pump power is equal to pump head times specific weight times flow rate. So I get pump head times specific weight times flow rate, and then all that divided by efficiency. Do I have the pump head? Yes, 80.3 meters. Do I have the specific weight? We said this was water at 20 degrees Celsius. What's the specific weight for water at 20 degrees Celsius?
$1,000.
The specific weight. Right? It should be 9810, right? I think 1,000 would be the density. Okay. Cool. And then the flow rate was 0.18.
Yeah.
My efficiency is 85%, or in decimals, 0.85. So So now, how much power does that pump require? 80.3 times 9810 times 0.18 divided by 0.85. We're going to have meters cubed. Sorry, go ahead.
Sorry, I was just going to say the answer.
Yeah, go ahead.
166,816.
Okay.
Yeah, I can hear it too.
So meters cubed cancel out. And we end up with newtons times meters, right? That's joules per second. What's joules per second? Watts. So we can just approximate this as 166 kilowatts. Does that make sense?
Yes.
Yeah.
Thank you. Are there any questions?
No.
No, that's the final answer, right?
Yeah, that's the answer for the pump requirement, right? It asked us to find the flow rate, which was 0.18, and then the power requirement, which is 166 kilowatts. Cool. I'm gonna stop recording